This lesson is on powers and roots of complex numbers when they're written in trigonometric form. You're going to find that at the beginning of this lesson we're going to use some of the concepts from the previous lesson on multiplying complex numbers that are written in trigonometric form. Let's take a look at an example. We want to find 1 minus the square root of 3 times I quantity squared. And I have a hint here to use trig form. I want to remind you, first of all, that when you square a number, that means to do what? It means to multiply that number times itself, doesn't it? So quantity squared means I'm going to multiply this complex number times itself. Let's put this number in trigonometric form, and then we're going to look at how we're going to find the square of this number. So recall, to find our value for r, we take the square root of x squared plus y squared, where we get x and y from our complex number. So x being 1, I'll have a 1, plus y is the square root of 3. Actually, it's negative square root 3. When I square that, I get a 3. So r is the square root of 4, which is 2. Okay? And then recall, for the angle, we write tangent theta is y over x. My y is negative square root 3. My x is 1. And as we've done before, I might refresh your memory again on the 30-60 triangle. If you have that labeled, the angle whose tangent is square root 3 over 1 would be 60 degrees. That will act as our reference angle. Let's notice that if we were to graph this complex number, x is positive and y is negative. So x positive, y negative puts us in quadrant 4. So if 60 degrees is our reference down there in quadrant 4, our angle theta is going to be 300 degrees. So in trig form, our number is 2 cosine plus I sine 300 degrees. So if I'm squaring that number, I'm multiplying it times itself. Now, in our last lesson, we learned that when we're multiplying complex numbers in trig format, we multiply the r's. 2 times 2 gives me 4. We do our cosine plus I sine, and then we do what? We add the angles. Well, 300 plus 300 is 600 degrees. Let me stop right here and let's examine what we have here. If I have 2 cosine plus I sine 300 degrees to the second power. Notice that I raise 2 to the second power to get the 4. But I take my angle and multiply by 2. Now keep in mind, although this looks like 2 times 2, if this had been a 5, I would say 5 squared is 25, but I would still just do 2 times the angle. Alright? Now, of course, we learned in previous form that if we have an angle that has revolutions, we take those revolutions out. So out of that 600 degrees, if we subtract 360 to get our revolution out of there, this will reduce down to 4 CIS 240 degrees. And then we can convert this back to standard form if we would like. So if I do the cosine of 240 plus I times the sine of 240. Recall that 240 is going to put you over here in quadrant 3, and you have a 60 degree reference angle, don't you? So the cosine in quadrant 3 is negative, and the cosine of 60 degrees is 1/2, so 4 times negative 1/2. And since the sine is also positive, the sine is going to be square root 3 over 2 times I. Then we'll distribute our 4. 4 times negative 1/2 is negative 2. And then multiplying here, the 2's will cancel, minus 2 square root 3 I. So we can square this number again. Once we have it in the trig format, we will square the r, and then we will multiply the angle by 2. Alright? Now, on our second example, notice it's the same complex number, but this time we want to raise it to the third power. Since we have already done the trig form of that number, I'm going to write here what we're looking for is 2 CIS 300 degrees raised to the third power. Okay? Now, I'm going to write this out just one more time for emphasis. If I have 2 CIS 300 times 2 CIS 300 times 2 CIS 300, I would multiply my r's. 2 times 2 times 2 is 8. I would write my CIS. I would add this and this and this. If I add 300, 300, and 300, I get 900, don't I? Notice again, if I take the 2 and cube it, 2 cubed is 8. But then I multiply. 3 times 300 gives me my 900 degrees. Okay? Now, once again, this 900 degrees has revolutions in it, doesn't it? In fact, it's got 2 revolutions. So if we subtract 720 degrees, which is 2 revolutions, we have 8 cosine plus I sine 180 degrees. In other words, 8 times the cosine of 180 plus I times the sine of 180. We know that the sine of 180 is 0. The cosine of 180 is -1. So 8 times -1 is -8 plus the 0I. So if we cube 1 minus the square root of 3 times I, we get -8. Now, having looked at these 2 examples, let's look at what's called de Moivre's theorem. If you have r times cosine theta plus I sine theta is a complex number, of course, in trigonometric form, and n is any real number, then r times cosine theta plus I sine theta, quantity to the n power. Remember, this is the same as r times CIS theta if you prefer that notation. If you raise a complex number in trig form to any power, you raise the r to the given power, but notice on the angle, it's cosine n times theta. You multiply that exponent times your angle, plus I times the sine of n theta. This could be written r to the n times CIS n theta. Now that we have looked at de Moivre's theorem, let's look at finding -1 plus the square root of 3 times I to the 5th power. Now, I think you might realize that to do this the old rectangular format where you do FOIL would be extremely difficult. You would have a lot of multiplications that you would have to carry out. But if we convert this complex number to its trig form and apply de Moivre's theorem, it will be very easy for us to do. So let's make the conversion first of all. Let's find our r. Square root, if I square x I get 1. If I square the square root of 3 I get 3. So r is the square root of 4, which is 2. The tangent of my angle theta is y, square root 3, over x, -1. Let's pay attention that if x is negative and y is positive, we're in quadrant 2, aren't we? What's your reference angle? Again, think your 30-60 triangle. You should have that thing pretty much memorized by now. Which angle has a tangent of square root 3 over 1? That's the 60 degrees. So 60 degrees is our reference. But we're going over to quadrant 2. So that means our angle theta would be what? 120 degrees. So we're going to convert this to 2 CIS 120 degrees, which we are raising to the 5th power. Okay, now de Moivre's theorem said we take the 2, the r, and raise it to the power. So I'm going to write this down for emphasis. I want 2 to the 5th. But on the angle, we multiply the exponent 5 times the 120 degrees. So 2 to the 5th is 32. And then I'll have cosine plus I sine. 5 times 120 is 600 degrees. Okay? Now, just like we've done before, we're going to convert this thing back. So let's take out the revolution. We have 32 cosine plus I sine 240 degrees. If you subtract 360 here, you're going to get 240. So we have 32 times the cosine of 240 plus I times the sine of 240. 240 again is in quadrant 3, 60-degree reference. So cosine and sine are both negative, the cosine of 60 being 1/2 and the sine being square root 3 over 2. Now when we distribute our 32, we get negative 16, notice the 2 cancels, minus 16 square root 3 times I. Do you see how easy it was to raise that complex number to a high power like 5th power? We could do that complex number to the 8th power, 12th power, just as easily simply by following this de Moivre's theorem. So I think you can realize how easy that makes finding powers. Now, let's talk a little bit about going the other direction. Instead of finding powers, we want to find roots. Recall that if you're doing a square root of something, let me just put a little sheet of paper up here so I don't mess this up. If you want the square root of 4, well, you might be thinking, well, that's 2. And the reason is because 2 squared equals 4. Keep in mind also that negative 2 squared gives you 4. So there are actually 2 square roots of 4, which we sometimes indicate by saying plus or minus in front of that. Notice I have said here find all of the cube roots of 8. Now you probably are thinking, well, 2 is the cube root of 8 because we know that 2 cubed equals 8. So we would say the cube root of 8 is 2. Well, it turns out there are 3 cube roots of 8. The other 2 cube roots, though, have a complex number form that we're going to be able to find. Now, the formula or the technique that I'm going to show you will, in fact, find all 3 cube roots of 8. Now, I want us to think about this. If you have a complex number, a plus bi, and you raise it to the 3rd power and you get 8, then a plus bi would be a cube root of 8, wouldn't it? We would say the cube root of 8 then would be a plus bi, because if we raise it to the 3rd power, we get 8. Think about in trigonometric form. You could rewrite a plus bi as some r times cosine theta. I'm sorry, not cosine, cis. I'm saying that wrong. R times cosine plus I sine theta. So r cis theta to the 3rd power, we're saying, is going to equal 8. Okay? Let's rewrite the 8 in its trig form. Okay? Well, let's see. 8 is the same thing as 8 plus 0i, isn't it? So the r for this would be the square root of 8 squared plus 0 squared, or 8. The tangent of theta is y over x, which is 0. And if you look at this, if you graph the ordered pair 8 and 0, your angle turns out to be 0 degrees. So it's 8 cis 0 degrees. Now, we just learned by looking at de Moivre's theorem, if I raise the trig form of a complex number to the 3rd power, what do? I raise the r to the 3rd power, but what do I do with the angle? I multiply that angle times 3, don't I? So here's what I have. R cubed times cosine plus I sine 3 theta equals 8 times cosine plus I sine 0 degrees. What is that telling me? That's telling me that r cubed must be 8, which says r is 2. But it's also telling me that 3 theta must equal 0 degrees. Well, you might be saying, well, then theta is 0 degrees. And so I have 2 cis 0 degrees, which is just equal to, and that's the cube root that you knew. But think about this. Wouldn't it also be true that 3 theta could equal 360 degrees? Because putting 360 here would be just like having a 0 there, wouldn't it? Well, look at this. If this 3 theta could also be 360 degrees, if we divide by 3, theta could be 120 degrees. So I would be saying 2 CIS 120 degrees. Okay? Well, let me show you something else. Instead of going 1 revolution, what if I went 2? Could I put, instead of 0 degrees, 720 degrees? Well, I would get the same values here, wouldn't I? So 3 theta could be 720 degrees. If I divide 720 by 3, what do I get? 240 degrees, I believe. So I could get a 240 degree thing here. Okay? Now, obviously, I could keep adding revolutions here, couldn't I? But I want to show you something. What if I go to a third revolution here? Let's see, 3 times 360 is 1080. So if I said 3 theta is 1080 degrees, that's 3 revolutions. Notice what happens when you divide that by 3. You get what? 360 degrees, which is the same thing as 0. Notice if we go 4 revolutions, that's 1,440 degrees. If you divide that by 3, you get 480 degrees, which is equivalent, if you take away the revolution, 360 degrees, it's equivalent to 120. It's the same as that one. So what happens in this process is your angles start repeating in terms of values. But I do want you to notice we're getting 3 distinct values here for our theta. Let's see what implications this has for our cube roots. Keep in mind I've got 2 CIS 0 degrees. I have 2 CIS 120 degrees. And I have 2 CIS 240 degrees. I have 3 distinct answers. Now, cosine of 0 degrees is 1. And of course the sine of 0 degrees is 0. So 2 times 1 plus 0i is just our 2. That's the cube root of 8 that you know. But let's look at this. 2 times the cosine of 120 plus I times the sine of 120. Now 120 degrees is over here in quadrant 2, reference 60. In quadrant 2, the cosine is negative, isn't it? And the cosine of 60 degrees is 1/2, so that's negative 1/2. In the second quadrant, the sine is positive. The sine of 60 is square root 3 over 2. So 2 times this gives me a negative 1, and multiplying here I get a plus square root 3 times I. You can check this out, but if you cube this number, you're going to get 8. Okay? So you can see it here. If you cube this, 2 cubed is 8, and if you multiply 3 times this, you get 360, which is going to give you the same values as that 0, so you're going to get 8. On this one, you have 2 times the cosine of 240 plus I times the sine of 240. Now 240 is going to put you over in quadrant 3. Of course, sine and cosine are both negative, but notice it's still what? A 60 degree reference, isn't it? 180 plus 60 is 240. So I've got 2 times negative 1/2 minus square root 3 over 2i. And when you distribute, you get negative 1 minus square root 3 times I. So here is a third cube root of 8. Now I also want to show you something that happens in terms of graphing these cube roots. Now I'm going to kind of try to keep all this where you can see this. For the cube roots of 8, we got 2. The second cube root of 8 that we got was negative 1 plus the square root of 3 times I, and the third cube root was negative 1 minus the square root of 3 times I. Okay? Let's graph those. Of course, 2 is the same thing as 2 plus 0i. So remember the ordered pair that you graph is 2, 0. So here's 2, 0. There's my graph of 2. The ordered pair here is -1, positive square root 3. Now the square root of 3 is about 1.7. So I would go -1 and about 1.7. And from the origin, go up to that point. The third one has an ordered pair of -1, negative square root 3. So I would go -1 and negative about 1.7 to graph that one. If you notice what appears to be true here, and it is true, these cube roots as vectors on this graph are equally spaced around my 360-degree circle. That will always happen. Cube roots of any number are going to be equally spaced. Now they won't all be in the same position. If I wanted to find the fifth roots of 8, I would get 5 answers and they would be equally spaced, all 5 of these equally spaced around my 360-degree circle. Now, having looked at finding these cube roots, I want us to notice that, first of all, when we found the cube roots of 8, 8 in trig format was 8 CIS 0 degrees. Notice if you take the cube root of this 8, you get the R that you need for all of the cube roots. For the angles, if we take 0 degrees and we add revolutions, I'm going to write it this way, 360 times k. So if I let k be 1, I'm adding 1 revolution. If I let k be 2, I'm going to add 2 revolutions. If I let k be 3, I'm going to add 3 revolutions. So I added revolutions. But notice what we were doing was finding 3 theta, so every time then to find theta, we divided by 3. This is going to lead you into a theorem that we call the nth root theorem. If n is any positive integer, in other words, we're not going to find negative cube roots or something like that, or it's got to be like cube roots, fifth roots, n is positive. R is a positive real number. Then the complex number R CIS theta has exactly n distinct nth roots. In other words, there's 5 fifth roots, there's 7 seventh roots, etc. Okay? The numbers in trig form. How do you find these roots? Well, notice here, you take the nth root of your R, whatever your R is here, and whatever root you're finding, you find that real number root. Then you have CIS, and I've got an alpha here. How do you find alpha? Well, you take your angle from the trig root of your number, from the trig form of your number, you add revolutions, you divide by the number here that agrees with the roots that you're finding. If you're finding cube roots, you're dividing by 3. If you're finding fifth roots, you divide by 5. How many revolutions do you have to add? Well, you start without adding any. You leave the original angle. You add 1 revolution, you add 2 revolutions. But recall in that example, at a point you start repeating. So how far do you need to go? Well, this tells you stop when k is n subtract 1. In other words, if you're doing cube roots, okay, 3 minus 1 was a 2. K would only go up to 2. And that bears out what we did when we did the cube roots of 8. If I'm finding fifth roots, n is 5. 5 minus 1 is a 4. So I would stop once I add a 4th revolution. Okay? Now, let's see how we can apply this nth root theorem. We want to find all of the cube roots of 27 cosine plus I sine 60 degrees. Now, this is already in the trig form. Since I'm looking for cube roots, my n is a 3. Okay? This is R, and this is theta. So, if I want cube roots, what I'm going to do is take the cube root of my R. That's 27. And I'm going to multiply that cosine plus I sine. Now remember, you start here with the angle given, 60 degrees. I'm going to add revolutions. So I'm going to add 1 revolution, 2 revolutions, etc. Since I am doing a cube root, I'm going to be dividing by 3. k is going to start out being 0, I'm going to start with the original number. I'm going to add 1 revolution. I'm going to add 2, and I'm going to quit here. Notice n minus 1. N is a 3, so n minus 1 is a 2. The other way I know to stop here is if I'm doing cube roots, there's 1, 2, 3 cube roots. So these 3 values of k are going to give me those 3 cube roots. Now we know the cube root of 27 is a 3, so let's write that down, CIS. Okay, let's start here. If k is 0, then I just have 60 divided by 3 is 20 degrees. That gives me my first cube root. Okay, for my second cube root, I'm going to take 60. I'm now letting k be 1, so I'm going to add 360 and divide by 3. So that's 3 CIS. Well, let's see. 60 plus 360 is 420. I'm going to divide that by 3, and I have 140 degrees here. Everybody see how I got the 140? Okay, for my third cube root, I've got my 3 CIS 60 plus. Now I'm letting k be 2. 2 times 360 is 720. Still dividing by 3. So I've got 3 CIS. Well, let's see. 60 plus 720 is 780 divided by 3 is 260 degrees. Okay? So is everybody with me here? Now, 20 degrees, 140 degrees, 260 degrees, these are not special angles. So if I want to get these numbers in standard form, I'm going to need to use my calculator. Since these are given in degrees, be sure that you're set for degrees. But before we find those, I also want to point out, notice between 20 and 140 degrees is 120 degrees. How many degrees is there between 140 and 260? Also 120, isn't there? You'll find out that these 3 cube roots are equally spaced 120 degrees apart all the way around our circle. Okay, let's get the standard form values. Okay, so I'm going to do 3 times the cosine of 20 degrees. And let's see, I think I'll keep 2 decimal places, 2.82 plus 3 times the sine of 20 degrees times I, that's going to be 1.03. So there's 1, and I should say, I guess this is approximate because we've rounded off. So there's one of the cube roots of 27 CIS 60 degrees. Okay, on this second one, we'll do an approximate value. I'm going to do 3 times the cosine of 140 degrees. That's about negative 2. I'm going to have to say it this way, negative 2.30. And then 3 times the sine of 140 degrees, and that's a positive number, so plus 1.93 times I. There's a second cube root, and then finally the third one, I'm going to do 3 times the cosine of 260 is about negative 0.52, and then 3 times the sine of 260 is a negative, so minus 2.95 times I. So these are the trig forms of those cube roots right here. And then here we have the standard form of those cube roots. But again, I remind you, once the number's in trig form, if I'm doing cube roots, I'm going to take the cube root of that. If I'm doing fifth roots, it'd be the fifth root. Then I'm going to do my cosine plus I sine. I'm going to write my angle down from the trig form. I'm going to add revolutions. I'm dividing that answer by the same number that agrees with the roots that I'm taking. And how many revolutions? Start with 0, then 1. Remember, you stop at n minus 1. So since n was 3, we're going to stop at 2. It also helps to keep up. If there's cube roots, there's 3. And so we know we have all the solutions. Okay, find all the fifth roots. All the fifth roots of 2 plus 2i. Now here, our number is not in trigonometric form. So the first thing we're going to want to do is to change that. So let's see, we've got r is the square root, x squared would be a 4, and y squared would also be a 4, so r is the square root of 8. Now I know that you can simplify the square root of 8, but I'm going to leave that in that form for right now. The tangent of angle theta is y over x, 2 over 2 is 1. Notice this is in the first quadrant. X and y are both positive, and the angle whose tangent is 1 is 45 degrees, isn't it? So in trig form, I have the square root of 8 cosine plus I sine 45 degrees. And we want the fifth roots. So there's going to be how many fifth roots? 1, 2, 3, 4. There's going to be 5 of them, right? Okay. Now, if you remember the form, whatever the r is, in this case this is r, if we're doing fifth roots, n is 5, I want the fifth root of r. So I want the fifth root of the square root of 8. I'm going to talk about that in a minute, about how to simplify. Cosine plus I sine. Now I want 45 degrees plus 0 to start out with, and what am I dividing by? I'm dividing by 5. Remember, the form was the nth root of r, cosine plus I sine theta plus 360 times k divided by n. K starts at 0, goes to 1, goes up to n minus 1. Since my n is a 5, my last number I use for k is going to be a 4. Okay. Well, let me talk a little bit about simplifying this before we do some of these other angles. Recall that the square root of 8 can be written 8 to the 1/2 power. Do you remember that? And a fifth root of something is to the 1/5 power. So if I have the fifth root of the square root of 8, I have the fifth root of 8 to the 1/2, or 8 to the 1/2 to the 1/5. And then if you remember your rules of exponents, if you have a power to a power, you multiply the exponents. 1/2 times 1/5 is 1/10. So what we're really finding is the 10th root of 8. Okay, now we may want to get a calculator value for that here in a little while, but I wanted you to see how we can simplify that radical format. Now, 45 degrees plus 0, of course, is 45. If we divide 45 by 5, we get 9. So I have the 10th root of 8 cosine plus I sine 9 degrees. That's my first fifth root. Okay, now on the second one, since we've already simplified that, we're going to do the 10th root of 8 cosine plus I sine. Now on this one, I'm going to add 1 revolution, so plus 360 degrees divided by 5. So I have the 10th root of 8 here. And let's see, if I take 445, oh, I wrote 450, I'm sorry, 445 degrees, let's get that right, 45 degrees plus 360. Guess I was thinking about that 360 and got that extra 0. 45 plus 360 is 405 divided by 5 gives me 81 degrees. Okay, all right, for the next one, 10th root of 8, CIS. Now remember, 45 degrees. This time we're going to add 2 revolutions. That would be 720 degrees, and we're going to divide by 5. Okay, so we have 45 plus 720 is 765. We're going to divide by 5. So I have the 10th root of 8, CIS, 153 degrees. Okay, we're getting close. 10th root of 8, CIS. Now I need to add 3 revolutions. Well, 3 times 360 is 1,080 divided by 5. So we get the 10th root of 8. And let's see. 1080 plus 45 is 1125. Divided by 5 is 225. Okay, and one more, the 10th root of 8, CIS, 45 degrees plus. Now notice we're up, we said 1 revolution, 2 revolutions, 3 revolutions. I'm now at 4 revolutions. Okay, so 360 times 4 is 1440. So I need to do 1440 plus 45. That's 1485 divided by 5 gives me 297 degrees. Okay? 1, 2, 3, 4. There's all the fifth roots of 2 plus 2i. Now, usually when it's given in the standard form here, you will want to convert this into a standard form solution. So what I'm going to do here is let's get another sheet of paper, and I'm going to kind of scoot this over to the side. And let's talk first of all about this 10th root of 8. Now, you may have a key on your calculator that will do nth roots. If you do not, remember the 10th root of 8 is the same thing as 8 to the 1/10th power. So you can use your y to the x, or if it's relabeled x to the y, whatever power, by entering 8, hitting this y to the x key, do a parenthesis, 1 divided by 10 gives you the power 1/10, and then do that. So that's what I'm going to do on mine, because I do not have a root key, but I do have that power key. So 8, and I'm going to raise that, and I need to use a parenthesis to get that 1/10 in there, or I guess you could put 0.1 if you want to. So this is approximately 8 to the 1/10 is approximately 1.23. Okay, so I'm going to use that 1.23. Okay, now I'm just going to use a parenthesis here. This means I'm going to do the cosine of 9 degrees plus I times the sine of 9 degrees, right? Okay, so let's do 1.23 times the cosine of 9 degrees. That gives me 1.21 rounded off, plus 1.23 times the sine of 9 degrees is about 0.16 if I round off times I. Okay? Now I could do the same thing with all of these other angles that we've done here and using the 1.23 for an approximate value. Now I might tell you that if you do this 8 to the 1/10 and you don't round this off, if you keep a lot more decimal places, your answers here may vary just a little bit, but we're getting approximate values of these fifth roots. I have one more example that I would like to do for you in this lesson, and actually it's a matter of solving an equation. Find all complex solutions of the following equation. X to the 4th plus 16 is equal to 0. Now, we might be thinking in terms of algebra. I could subtract that 16 and get down to this point right here, couldn't I? X to the 4th equals negative 16. Well, in order to find x, what I might want to do then is take the 4th root of negative 16. Now, you're probably thinking, you can't do that because there's not a number to the 4th power that is negative 16. And you would be correct in terms of real numbers, but that is not correct in terms of complex numbers. Notice find all complex solutions of this equation. We have just learned how to find roots of complex numbers. So let's think about this negative 16. Negative 16 is equivalent to negative 16 plus 0i. If I change this to trig form, r is the square root of, well, if I square negative 16, I get 256. And if I square 0, of course I get 0. Well, the square root of 256 is 16. Think about the ordered pair here. Negative 16, 0. Where would you graph that? Negative 16, 0. So your angle's what? 180 degrees. So negative 16 plus 0i is equivalent to 16 cosine plus I sine 180 degrees. Okay? Now, I want the fourth roots. So my n is a 4. Okay? So I want the fourth root of my r, the fourth root of 16. Cosine plus I sine, I want my angle 180 degrees, plus I want to add revolutions. Since I'm doing fourth roots, I want to divide by 4, and what do I want k to be? Start with 0, 1, how far do I go? Since my n is 4, n minus 1 is a 3. Now notice 1, 2, 3, 4 answers is what I'm going to end up with here. Okay? Well, let's see, the fourth root of 16 is a 2. CIS. Well, if k is a 0, this is not there, 180 divided by 4 is 45 degrees. Okay, so there's one answer. Okay, what about the second answer? Well, the fourth root of 16 is a 2, CIS. If I let k be 1, 180 plus 360, 180 plus 360 is 540. If I divide that by 4, I get 135. Okay? Third answer, 2, CIS. For this third answer, I'm going to let k be 2. 2 times 360 is 720. So 720 plus 180 is 900, divided by 4 is 225. And then finally, my last answer, 2, CIS, I'm now letting k be 3. 3 times 360 is 1,080, plus the 180 that you have right here is 1,260, divided by 4 gives me 315 degrees. Okay, so I've got all 4 solutions. If I have x to the 4th, I should have 4 solutions. Now, you might recognize that 45 degrees is a special angle. The cosine of 45 degrees is square root 2 over 2. The sine is also square root 2 over 2. So I have square root 2 over 2 plus square root 2 over 2i. If I distribute my r of 2, I get square root 2 plus square root 2i. Now, 135 degrees puts you over in the second quadrant. Notice the reference is still 45 degrees. So if we're in the second quadrant, what's true? The cosine is negative, but the sine is still positive. So on that one, I get negative square root 2 over 2 plus square root 2 over 2i. When you distribute your 2, you have negative square root 2 plus square root 2i. Okay, what about this 225? If you go over to the third quadrant with 225, 225 minus 180, guess what the reference still is? 45 degrees. In the third quadrant, the cosine and sine are both negative. So I have negative square root 2 over 2 minus square root 2 over 2i. And when I distribute my 2, negative square root 2 minus square root 2i. And finally, 315. Well, as you might guess, 315 brings you over to the fourth quadrant. Reference is still 45. In the fourth quadrant, the cosine is positive, but the sine is negative. So you have square root 2 minus square root 2 over 2i. And distributing your 2, we get square root 2 minus square root 2i. Now, I might want to show you something here. Notice square root 2 plus square root 2i, square root 2 minus square root 2i. Those are conjugates. They're just alike except for the sign between them. Notice these two. Minus square root 2 plus square root 2i minus square root 2 minus square root 2i. Those are also conjugates. Turns out that the roots appear in these conjugate pairs like that. And again, since we were doing fourth roots, they're going to be equally spaced. Remember how we talked about that? So it's not surprising that all of them have that 45-degree angle as a reference angle since they're equally spaced. Now, the key thing to remember, whatever root you're finding, you're going to do that root of your R. And then on your angle, you take the angle of your number in trig form, you add revolutions, starting with k equals 0. So you start with the original angle, add 1 revolution, add 2, you keep going until how many? Well, the number of revolutions is always 1 less than your root. You add those first, then divide by your number down here, which agrees with the root that you're taking. Finding these roots can sometimes be tedious, particularly if you're asked to find 5th or 6th or 7th roots, because there's so many of them to find. It's also nice sometimes if you can leave your answers in the trig form and not have to go back to the standard form. I want you to remember in this lesson, raising complex numbers to powers is easy if you're in the trig form. You raise the r to the power, you multiply the power times the angle, because it's just repeated multiplication. When you're doing the roots, you've got to get it in that trig form and then remember that formula that we have just talked about. This completes the lesson on the roots and powers of complex numbers.